Section 5.4, Part 1. Section 5.4 is talking about exponential functions, particularly the function y equals e to the x, and then later a to the x. Part 1 will be differentiating, and then Part 2 will talk about how to integrate. So, first of all, let's look at the function natural log of x. Here's the graph. It looks like it's strictly monotonic, and so it must have an inverse. So if you project that, we've got the line y equals x, and you flip that over here, reflect it over the line y equals e to the x, we've got this inverse function. Well, this inverse function is a function called the natural exponential function. It's y equals e to the x. E is a constant. It's a number like pi that is irrational. It goes on forever. It's a decimal. It has no pattern. So f of x is natural log of x, and then its inverse is e to the x. So these two functions are inverses of each other. All right. So let's examine that a little bit more. So Leonhard Euler, our German mathematician, was the first mathematician to use the symbol e. He was talking about the base of natural logarithms in a letter to another mathematician. Because remember, the natural log of x is just a shorter way of writing that. And so that's Euler's number. We've talked about that before. So the inverse relationship here, if we do here's the definition of the natural log function. If f of x is natural log of x, the inverse of it is the natural exponential function. This is the way we denote it. So y equals e to the x if and only if x equals natural log of y.
I went to the clinic again.
Okay, sorry about that. So remember to show an inverse relationship. If you put one function inside of the other, it should equal x. And so we are defining the natural log of e to the x as x. Remember what you can do with exponents when you take the natural log of something. You can put that x out in front. So if we rewrite this side as x and then times natural log of e, if that's supposed to equal x, then what is the natural log of e? Well, we already talked about that when we first talked about natural log. Isn't the natural log of e 1? So that makes sense. X times 1 is x. Here, this is going to be very helpful for us. E to the natural log of x. Basically, if you put natural log in the exponent of e, they undo each other, and then that just equals x. So e to the natural log of x would just equal whatever that x is. So like e to the natural log of 4 would just equal 4, or e to the natural log of 10 would just equal 10, because they just undo each other. That's going to help us solve some equations. So let's do an example like this. If we want to solve 7 equals e to the x plus 1, we want to solve for x, so we want that x out of the exponent. So let's take the natural log of both sides. So now these two undo each other, and that exponent will be out in front, so we'll just have x plus 1. Okay, two ways to think about it. Natural log of e undo each other, and you're just left with x plus 1. Or you can flip that exponent out in front, and then you'll have x plus 1 times natural log of e, which is 1. Either way, you just end up with x plus 1. And here we have natural log of 7, so we subtract 1, and the exact answer is natural log of 7 minus 1. How about if we want to solve natural log of 2x minus 3 equals 5? We want to get that x out of a natural log. And you can't like distribute it in or anything, so we want to get rid of the natural log. To get rid of natural log, you do something called exponentiating both sides. You raise each side as the exponent of e. So the exponents are the original equation, and we've exponentiated both sides. They are each the exponent of e. So now these two things cancel each other out, and you're just left with 2x minus 3 on this side, and this is some number, e to the 5th power, whatever that is. So continue solving. So 2x equals e to the 5th plus 3, and then divide by 2. So the exact answer for x is e to the 5th plus 3 all over 2. This is supposed to say operations with exponential functions. Just the same rules that we used for anything with exponents apply to e. So e to the a times e to the b is e to the a plus b. E to the a divided by e to the b is simplified as e to the a minus b. Same rules that we've used with exponents before. let's look more closely at that natural exponential function. It's this graph. We have already talked about that where we reflected it over the line y equals x, and that was the I was supposed to hit 1 there. That's the natural log function. This is e to the x. Some key points to notice is e to the 0 is 1. The domain is all reals. The range is all positives, so the y values will never go below the x-axis or even touch the x-axis. F of x equals e to the x is continuous. It has no sharp turns, no jumps, no holes. It is increasing and 1 to 1, so it's strictly monotonic. The graph is concave upward everywhere, and if you take the limit of e to the x as x approaches negative infinity, so going this way, as x gets lower and lower, the limit is 0. As you get x's higher and higher, the limit is also getting higher and higher, so infinity as x approaches positive infinity. Just some properties. You will have to know the graphs of natural log of x and e to the x by heart, so be familiar with these key points here and the asymptote here, so that you know this natural log of x never goes beyond the line, the y-axis, and the e to the x never goes beyond the x-axis. So make sure you know how to memorize those graphs and are familiar with them without a calculator. All right, so here's the calculus. Derivatives of the natural exponential function. It's really awesome because the derivative of e to the x is just e to the x. The only complication is if you have the derivative of e to some function, so e to the u, it's not just a plain old x, but it might be x plus 7 or 2x squared or whatever, then the derivative is that e to the u, but then times the derivative of the exponent. So the derivative of e to the x is pretty easy to memorize. So let's do this example. If we have the derivative of e to the 2x minus 1, that will be itself, and then times the derivative of the exponent. So I would write my final answer like this. Pretty easy. How about this one? So I would rewrite that exponent as negative 3x to the negative 1. The derivative of it, multiply, and then subtract 1 from the exponent. So that equals positive 3, over x squared. So now the derivative of e to the negative 3 over x is e to the negative 3 over x times 3 over x squared. So I would write that as 3e to the negative 3 over x squared, like that. So that's your final answer for the derivative of that. Okay, if they ask you to find the relative extrema, we're just taking the derivative, setting it equal to 0. Same process, but we have a new part to our new function to deal with. So take the derivative. We're going to need a product rule. This is u and this is v. Derivative of the first times the second plus the derivative of the second times the first. And so that simplifies to e to the x plus x e to the x. We want to set that equal to 0. So we can find critical numbers. So we're going to factor out what we can. So we'll factor on e to the x. Set each factor equal to 0. And we know that the domain of e to the x is all reals, but the range is positives and not ever equal to 0. This will never equal 0. So that will not produce any critical numbers because e to the x can never equal 0. Here, if we subtract 1 from both sides, we get x equals negative 1, so that's our critical number. So if you like a number line or you want to do intervals, pick a number in the interval from negative infinity to negative 1, like negative 2. Put that into the derivative. So that's this or this, but in fact the factored form is a little easier. 1 plus negative 2 is a negative number. And e to the negative 2 really just means 1 over e squared. So that'll still be a positive number. So we have a positive number times a negative number. So that will be a negative derivative. So if the derivative is negative, that means that the function is decreasing. Here from negative 1 to infinity, what if we put a 0 in to the derivative? So we'd have e to the 0. E to the 0 is just 1. So we have 1 times and then 1 plus 0. So a positive times a positive is a positive. So if your derivative's positive, that means your function is increasing. So this function has a decreasing segment and then the increasing segment. So at -1, we must have a relative minimum. So the relative minimum is -1, and then we got to find the y value. To find a y value, you plug that x into the original function. So that's going to be -1 times e to the -1, which is -1 over e. So that's our relative minimum. There's your homework.